Good afternoon, ladies and gentlemen. Are you still awake? Yes, you're here? So let's have 1 hour, and then I promise you get an excellent coffee and some tea and some cookies and some food, so don't worry. So we will take care of you. My name is Markus Kalo. As you already said, I'm an architect and civil engineer at the University of Delft in Holland. And I've been working with integration of design for the last 10-15 years. So it's quite a while, and amongst others, what I did, you can lower the microphone a little bit, please. If I can speak up a little bit. Yeah, thank you. So the companies I've been working around with for quite a bit is, amongst others, Citizen M. It's a hotel company where we increase the comfort to the maximum possible. But also companies like Accor Hotels, or cost efficiency on a company like Lidl or Debenhams, where we actually reduce the energy performance, reduce the energy usage of Debenhams about 35% on average for all the future stores compared to the old stores. So that's part of the integrated design idea. So when we talk about integrated design, I believe it's a necessity for the future buildings. I mean, we today need to design the buildings for tomorrow, the demands of tomorrow. Petra talked about EPBD, energy directives. You talk about energy getting more and more expensive. I know you have cheap gas in Russia. I know you have still quite cheap electricity. But all these prices go up because of the demand going up. So the question would be, if we talk about integrated design, when we design a building with architecture and then with the civil engineers and the technicians on your side, when are these two sides meeting each other? I mean, should it be architectural design versus HVAC design, HVAC for heating, cooling, ventilation, or should the HVAC design like normally happen after the architectural design is done, or should it actually be an integrated concept from the very beginning, which combines the aesthetics, the technical design, and also the costs? Now, if we look at the main questions that we have, it's of course, how do different types of building are affected by this? What does it mean if you have technology in a hotel or in an office building or a school? What about strong or weak architecture? If you have got a famous architect that doing fantastic work, how will that interact with the technical equipment that you will have to put into these buildings? How much space do you actually need in the different building types to have a good installation? Because there's ratios that make sense and others that don't. And we'll come back to that later. And how can I have a building that is both sustainable on the environment side, but also economically feasible? So that's actually interesting for all parties to construct, to build, and to run these type of projects. And of course, what kind of advantages can I have in this early integration? This is what we're going to talk about today. So if we were talking about integrated design, what is that? Well, a long time ago, integrated design could look like this. This is a Pont du Gard in France. Of course, it's integrated because you've got partly the water transportation coming from the lakes to the big cities. But of course, you also have crossing the river. You have the road passing over. So it's a design that has multiple functions. If we come to a little bit closer to today, you know, want to see an integrated design, maybe not done by Volvo. It could be like this, no? Yeah. Integrated design? Early design. Early design. But today, what you talked about, Morgan, of course, is the Internet of Things. That's really the future, where everything gets integrated. I think, Morgan, I don't know if you mentioned, I think there's 3 billion devices today that are connected to the internet. And I think this is gonna be like times 10 in a couple of years. So that's gonna go up, like you say, your fridge, everything will be connected. And of course, that's a new part of how to integrate a design. Now, if we look at the definition for us in this room for the building industry, for the HVAC industry of integrated design, what you could say is that we combine the concept of architecture with the different architectural stages and the construction stages from the very beginning, with the installations, with all the technology aspects of the building. And so we work together with the installations and the architects from the very, very beginning. And by that, we actually look at the building type, we look at the climate, we look at legislation, and we look at the special requirements for the different uses. But this is really, really small text. I think they have some problem with the technology, but it's, I hope you can read it a little bit. So it's. Now, if we talk about sustainability, it's sometimes confused with environmentally friendly. Of course, that's true, but that's only one part. If you want to be sustainable, it's not enough to be environmentally friendly. It also has to be fitting to the economical situation that you're in. If you make something extremely environmentally friendly but too expensive, it's still not sustainable. And it also has to fit the needs that you have. I mean, you cannot have a bad indoor climate, or you cannot have a bad disposal of use in a data center. It has to be fitting to the needs that you actually have as a user to be sustainable. So sustainability really consists out of those three parts. If we talk about integrated design, of course, on the buildings level, we have three levels how to save energy. The first one is the building shell. This building shell could be concrete, could be wood, it could be aluminium, steel, glass, whatever. And of course, the quality of this building shell will be very significant on how much energy you're actually going to consume. It's the material, it's the orientation of the building. It's how many windows do you have? Do you have solar shading? What type of tightness, how airtight is the building? And of course, solar shading in the type of glass is very important. Just to give you an example on the quality of glass. On the winter time, it's very nice with a good U value, but the U value doesn't matter basically in the summertime. In the summertime, it's the solar factor, how much energy of the solar thermal energy you keep outside that you want to control. So you don't want to get more than 40% of the energy to get into the building. Otherwise, you raise the amount of cooling you need, and that costs you a lot of money. Now, what about glass? Modern architecture, we sometimes believe we need to have glass at all costs. We produce everything with glass, and it will have a lot of trouble with that, and a lot of cost around that, without any really need. Because, I mean, this is a quite typical situation, and I don't know how you like to work in your office, but when I came to St. Petersburg last summer, somebody was working like this, and maybe that's not the idea, no? So it's not always good to have a maximum of sunshine to come inside your building. So of course we have to have the right balance with glass. I mean, you could have this whole facade. This is a building, I think, in Tallinn, where basically the day the building was put into use, all the solar shades came down, and they have never come up ever since. And of course, the solution is not to build something like this. Do you know what this is? It's the Federal Reserve in New York. That's where they keep the money. That's why they don't have windows. But you don't really want to work there, right? So you should find the right balance, of course. So how we use glass, and if we use glass, we have to use the right quality. And it's of course also important to understand that the solar angle has a very important effect here. If you take a typical building in St. Petersburg, you take an office building, when do you think during the year will be the highest cooling need in that building? Which month? Anybody? July? Because it's the hottest time of the month? That's the most popular guess, but I'd have to tell you, sir, the biggest use of energy probably for cooling will be either in September or in March, end of March. And that's because of the solar angle. The sun comes much lower into the building and will heat up all the surfaces and will heat and store up all of this. So if you make a simulation on the climate, you realize the outside temperature in September is probably just 16, 17 degrees. But inside it goes away to 25, 26, 27. While in July, when it's 24 outside, average in St. Petersburg, you still have 25, 26 inside. So because the sun is much steeper. And that's quite interesting. That's also true if you look at a standard office, double office room in St. Petersburg. You need to install roughly 900 watts of cooling power in a room. Now, if we go far south in your big country, we go to Krasnodar, okay? How much energy you have to install in Krasnodar in the same room, do you think? How much more? How much less? What do you think? 20%? 30%? Actually, the number of Krasnodar is 989. It's not even 5% difference. So why is that? Same reason. You have the solar angle. You see here in Krasnodar, it's 68.4. In St. Petersburg, it's 53.3. So the sun sits lower in St. Petersburg, comes deeper into the building, so you need more cooling power, but it's less hot outside. So the same type of office in Krasnodar as in St. Petersburg will require roughly the same amount of cooling, believe it or not. So that's quite interesting. Now, of course, you have to find the right solution. If you're a technician, you can have fantastic technology, but you have to apply it the right way. I find this is quite a funny picture because you see the sun, but you also see the reflection of the sun in the solar panels. So what's that? Solar panels to the north? Well, they won't work too well. And it's the same thing. If you have to be exact, you can be exactly wrong as well. If you build a bridge and you don't have your coordinates right, this is what's happening. So, of course, you don't really can rely on technology on the details. You have to find the right application as well. The second step of reducing energy after the building shell would be on the room level. And here we come into what was referred to earlier as demand-controlled heating, cooling, ventilation, lighting, and so on and so forth. You see, this is the same room in different times of the day. You can choose when to light up the room, when not. You have to have absence control, both for lighting and installations. You do not want to overventilate the room. You don't want to undercool or overheat the room. So that will all cost you a lot of money. And of course, that means you want to have a climate distribution on demand for heating, cooling, and ventilation. And that's why we say control matters. So you have to have the occupancy and the air quality control. So what you want to do is you want to reduce the temperature in wintertime, for instance, if nobody's in the room. Normally 1, 2, 3 Kelvin. In the summertime, you will let the temperature go up, maybe 1 or 2 Kelvin, when nobody's there. So if you accept 25 degrees in summertime in occupancy, you might accept 26, 27 degrees when nobody's there. If you accept 20 degrees in wintertime, well, maybe you can expect 19 or 18 degrees if nobody's there. This is especially interesting for buildings like hotels, for instance. Well, most of the day, nobody is in the room. But of course, the sun is shining and you could keep perfect indoor climate. For whom? Nobody's there. Because the businessman checks in at 5 o'clock. He goes for dinner. He goes back, sleeps there. Next morning, he checks out 9 o'clock. And then you have full climatization during all day when nobody cares. Or nobody could complain. That costs you a lot of money. And of course, then the next step of reducing energy would be on the central level. On the central level, you have the energy recovery, both on the air, on the heating, on the cooling, on the humidity. You have to have the balanced air volume. I know still in a lot of buildings, you might want to overpressurize the building because you don't trust the building to be airtight. What happens then is all the energy you put into the air or into the water or whatever will be pressed out of the building. If you have 10% overpressure, you're putting 10% cooling or heating into St. Petersburg, but not into the building. On top of that, you will press out moisture into the construction, helping for nice fungus and mold and this kind of things to grow. The Accor Hotel Group had to refurbish over 5,000 hotel rooms because they were working on overpressure. Now imagine you're standing there in the shower and you're producing all this humidity and then you press it into the walls. Becomes a very smelly situation after a couple of years. And quite unhealthy on top of that. So of course you want to be exactly right dimensioned as well on the energy carriers. We're talking about the right size of ducts, the right size of pipe work, the right signals for BMS, for electronics and so on. That's extremely important. And of course, we, by that, reduce the primary energy need. That means we reduce how much energy we need to buy and purchase. So that's good for our environment and that's good for our pocket because we save money. So efficiency matters. air handling unit, cooling, heating, efficiency of chillers and heat pumps, COP, EER. This is all important. And a low SFP, so specific fan power, to work with low pressures in the system. So if we look at the integrated design in a building, you have the high quality building shell, step 1, keeping the energy where it should be. You have the demand control to have the right amount of air, heating, cooling, ventilation in each and every room. And then you have the high efficiency and high recovery energy producers or facilitators like air handling units, chillers, heat pumps, district heating, and so on and so forth. And if you only remember one thing from this seminar, the rule of thumb when you control media you should remember is always work with as low pressures as possible, both on the air side and on the water side. So you rather want to regulate the air volume, the air amount of air, by regulating the fan than by regulating a damper. Because if you regulate a damper, you create pressure. If you by slowing down the fan, you save energy. It's exactly the same on the water side. You rather want to regulate the pump than to close a valve. I mean, you all have these thermostatic valves in your home. So you have very, very hot water coming from your gas system, 80 degrees, and then you close the valve almost 100%. So the pump has to work really, really hard to press little bit of 80-degree water through your radiator. While instead, this thing could be open, and the water that goes around could be flowing easily, almost by itself, in 40 degrees, producing exactly the same heat in your room, but at a much, much lower cost. This is true in your home, this is true in a data center, this is true in a big office block. It's always true. Now, if we look at the difference of strong and weak architecture in this concept, if we say we have the architecture that starts from the beginning, and then we have the integration of design, the installation on the other side, this part where it actually interlinks, this is what I call the integration of the design. Now, if we look at different buildings and examples how well integrated they are, we could start with this. Anybody know where this is? Beautiful picture, huh? I hope none of you lives like this. I did for 6 months. It was not too funny. This is actually in the Paris suburbs in France. And you see these circles, they don't even meet. We don't talk about integration of anything. And there's almost no architecture and there's almost no installations here. So you have cheap functional architecture. It's looking bad, it's smelling bad, has no ventilation that works. It's a lot of space, but no flexibility, no comfort. And you have a lot of short-term and long-term problems with this solution. And high running cost, of course. And life length is very limited. And you also get the problem with smell of fungus and mold and stuff like this. So I give you an example how the system works or doesn't work. You see, you have these cold thermal bridges here that go, the concrete slabs that go right outside from the inside. And here you see where the humidity comes down on those cold bridges, you get all the mold and the mushrooms growing. So that is what we call also sick buildings. You get asthma and allergies and all these kind of things. And of course we have the supply air grills. They're often closed off because they make draft in the apartment. And then what you get, you can start making your own botanic garden inside, right? Now, an extract air system is a problem because if you see how this works, you take in the air around the window, for instance. You get in all the noise from the traffic outside. You get in all the sound emission into the building. Of course, you also get in all the smells from the traffic, from the neighbors, from cigarettes, whatever. And on top of that, you have the draft of the cold air coming in and not making this room too comfortable. You might argue, well, yes, but I have got this heater that is Coanda effect and it will take care of that. Might be true if you're lucky in winter time, but what happens in spring and autumn? Now the heater is turned off and this cold air will just fall down onto the floor, and make a totally cold and uncomfortable floor. Okay. So this is even a situation in completely new constructed apartments in Stockholm we see right now. Now, if we look at the energy cost for this kind of system, this is just a big sheet of when you compare the energy use of extract air system with a system with balanced air volume and energy recovery. And what you will see is the energy saving is 66%. So 2/3 of the energy is saved by having a balanced air volume system with recovery. So this is quite a bit of money. So in this apartment block of 100 apartments, you have 72,000 euros of 72,000 euros of annual saving every year. So that is extensive saving. Next example, we have beautiful architecture, limited or, in the beginning at least, questionable HVAC or installations. And you will wonder why, but this actually is the Swiss Re in London. You know this building? Very famous. Norman Foster Architects, brilliant. Very good idea, very good concept, including ventilation also. But there is one problem, and that was about sustainability on the social level. Now have a look at this. You have these atriums bringing the cold and the hot air and making this natural ventilation all around the building, in theory. This would have been fantastic if people would behave according to architects. But now architects have to behave according to people, because imagine, these are the different floors. And you know where this building is? It's central London. It's Bank Street. It's the most expensive square meters in the world. Now, this is one bank, and this is another bank, a competing bank. Do you think they're going to talk about their business in an open space where all the competitors can listen in from the balcony below or balcony above? Won't happen. So the first day this building was occupied, they closed all these situations off with glass walls. And as soon as they close it, no more natural ventilation. So the concept was good, as long as you wouldn't be talking about bank secrets of competitors on the different floors. So of course that's a problem. So how did we enhance this situation? You see here is a central air handling unit on each of the floors. I think there's 40 central air handling units, which occupy the core of the building. That's also a problem, because that's a lot of square meters that are lost. So what happened is, we made a new design. We have these central air handling units in the ceiling, on top of every office finger, basically. There's 6 of them on each floor. By that, you can actually have demand control ventilation. You might maybe need more air on this area than here, because here you have a lot of conference rooms, and here's just some people working. It's different companies already. So you can be much more flexible in the use. On top of that, you see, this whole central space is now emptied. So they can actually use it as rentable square meters for the coffee machines, for the copy machines, for the fax machine maybe before, for storage, and so on and so forth. For all their files that you have to have, it's all there. So what happened, of course, we increased the ventilation, we reduced the cost. We have more cost on the air handling units, of course, but we freed 1,000 square meters of rentable space. Do you know how much that is? That is 12 million euros of extra rental revenue on 15 years' time. So it doesn't matter if your equipment costs double or half, because that money is much more than your equipment ever costs. So don't be cheap on what you install, rather save cost around your products. That's much more clever in this situation. Next example. Weak architecture, strong HVAC, very strong HVAC. Now, you have a fantastic indoor climate. You have no respect of the building at all, no aesthetics at all. And this building would be terrible if it would be the first of its kind, because it's the first time ever. Everybody thinks, oh, it's fantastic. Centre Pompidou, you know it? Okay, would you want to live in this building? Maybe not. Would you want all our buildings to look like this? Maybe not. So maybe, of course, you should not have installations being so exposed. So, basically today we believe that the installations should serve our purpose and not be the purpose, of course. And it's important to understand that a typical installation space inside the building, not outside the building, is related to the building type. And as an example, in a retail building, like a shop, you need to allocate about 8% of the floor space for installations. In an office building, it's between 9 to 11%. In a hotel, it's about 17%. If you don't respect these numbers, you either will have too big space, you will lose square meters to rent out. But if you make it smaller, you have no chance for the pipe work, for the duct work, for the maintenance to work, to have efficient machines, to have efficient SFP, COP, EER. All of this is not possible if you have too little space. So these numbers you should try to remember and to work with them from the very beginning in the integrated design. If the architect doesn't know there's 17% in this hotel he has to sacrifice for all the stuff that you do and that he doesn't like, he has a problem. And we talk about with architects, you have this beautiful ray of light, windows and high ceiling, and then you come with a 600 millimeter Spiro duct right through everything and destroy it. You won't be too happy. Or the architect designs a fantastic, beautiful looking hotel room, 5-star, with flat screen TV and a soft bed and 20 pillows. Fantastic. And then you have an 8 meter per second riser ductwork in the bathroom. You know how that sounds? All night. You sleep well? Maybe you do. I prefer to be silent. So of course you have to have enough space for that duct for the air to go slower, to not create that sound. So that's what I talk about, integrated design. Now, we have an example of beautiful and strong architecture with maximum integration. And Petra was already discussing this. As an example, it's the Oslo Opera House. So what we see here, it's a beautiful building, I believe, with a perfect indoor climate. You have a maximum flexibility for different use in different time of the day and the year. And you have a lot of short-term and long-term advantages, both on the energy bill, on the comfort, on the adaptability, on the flexibility for the future. And so you can use this for many years. I give you some examples. You have the facade that is very representative directly on the water side. You have perfect indoor climate, completely silent and well cooled and ventilated for the concert hall. And you have a lot of areas with variable use. I mean, this is all the exercising rooms for ballet and so on, that sometimes there's 200 people and sometimes there's 2 people. And of course, this creates different needs for heating, cooling, and ventilation. Of course, you have the solar panels. Of course, you have intelligent solar shading on the facade by controlling to get the energy of the sun when you need it in wintertime and to keep it outside when you don't want it in summertime. And of course, we have the technical details, like to bring the air in under the chairs in the auditorium, very low speed, cold air coming up in your body, making it completely comfortable, silently, without too much speed. This is important details for you to see, but it's part of the whole design of this building. Now, some of you might have seen this before. We have 2 air handling units here. One is installed in 1988 and one is installed in 2015. And I have to ask you here, which of these air handling units is using less energy? What do you think? Anybody? Which is using less energy of these units? The right one? Something to do with PM vent maybe? You might be right, but no, sorry. It's this machine using less energy. You know why? It's broken. It's using 0. Okay? And the point is, good indoor climate will always cost you money. It's not for free. Of course you can save, like you said, you can cheat. You can say, I make this indoor climate terrible inside here. It's very cheap. But that's not what we're talking about. You will have to pay for good indoor climate. And if you don't, you will get this problem with the tight buildings. And again, you will have your mushrooms. And it will smell. You won't like that. And I don't know if you have thought about the indoor climate in this room. Is it good climate inside here? Is good? Are you cold? Are you warm? Are you fine? So, a little bit cold? Okay. So as soon as something is wrong with the indoor climate, you realize it. Or maybe you hear the projector. Or maybe it's interfering with the loudspeaker. It's something with the sound or the smell or the temperature. You realize. As soon as it's perfect, it disappears. You don't think about it anymore. And again, that's important for architects. If you want to appreciate this beautiful room with the chandeliers and the stucador and everything, you cannot be freezing or smelling or having sound problems because you will not like the architecture. So good architecture and good indoor climate, they belong together. And if it's even good for your pocket, it's even more important. Now, some rule of thumbs for different building types. This might be interesting for you. You are different. You are in construction. You are in consulting. And if you have some of these rule of thumbs, that might actually help you how to look at these building types. You will see the amount of air that is required is different in both for ventilation, for retail, and for schools, as an example in this case here, per classroom or per square meter in a shop. The sound level is roughly the same, 35 decibels, because people are working. You normally acclimatize with air, heating with air, cooling with air, while in the school, it's normally with the radiators, with water. You will allow temperatures which are quite 24 in the summer, 21 in the winter, and the other one is a little bit higher in the school. Demand controlled, of course. And of course, you need roughly about 8% for installations in the retail. You need about 12% in the school for all the installations. If you instead compare hotels and offices, something happened with the picture here, sorry. You will see that you need about 1 or 2 air changes per hour in a hotel room. It's about 80 cubic meters per hour. While you need about 40 cubic meters in an office. Now, sound level, that's interesting. In a hotel, it's maximum 25 decibels. In an office, 32. Why? Well, hopefully you don't sleep in your office. Okay? So, of course, you can accept a higher sound level in the office because also your computer will make noise and so on. So it won't be as critical. Now, both are working with water or DX. But the temperature is a bit more critical in the hotel room because you're lying still in your bed, so you cannot have any draft, for instance. It has to be demand controlled in the hotel because you're often not there during the day. Well, often in the office it could be demand controlled or standard. And you will see in a hotel you need much more space for the installations because this is not just ventilation. This is also sewage and this is showers and all this kind of things, you know. Well, in the office it's roughly 10%. And you see about 10 plus 20 square meter per person, while in the office you have about 10 plus 5 square meter per person. So you need more space in the hotel. So, indoor climate matters. And when we talk about indoor climate, we don't talk about temperature only. We talk about smell, air quality, humidity, and so on. We talk about energy efficiency. You mentioned EPBD, you have BREEAM, you have LEED in the US, you have Passive House, you have all these certifications, green building. But they're all about the same thing, to reduce the amount of primary energy per square meter and year. And this could be either for the environment or for the amount of money you pay every time. So what you need to know about energy? First of all, which energy do you have? In Russia, for instance, you have a lot of gas. Do you have oil? Do you have district heating? What is available for you? You have to know the cost for the different energy sources. Well, if you want to make any comparisons, here, this is the numbers for Russia, I think, that come. No, they don't come up down there. Something is not working as it should be. But you have to know how much is the kilowatt hour of electricity. How much is it for gas? I think you pay 90 euros per 1,000 cubic meter of gas. you pay only 3 euro cent for kilowatts per electricity. So it's quite cheap with gas electricity in comparison to other countries where they have a lot of taxes. But then it might be availability, which is interesting. What does the legislation say about that? What about monopoly? If there's only one provider, can he put up the price and down as he wants? How dependent are you on that? And of course, do you have any need of simultaneous heating and cooling? I don't know about Russia, but I know how a standard office building in Stockholm looks like. In autumn and spring, you have simultaneous need of heating and cooling, right? You need to cool towards the south. You have to heat during the north. So you buy actually 100 kilowatt of district heating from the city, and you put into the building for one part of the building. At the same time, you buy 100. You actually have a chiller on the roof, producing 100 kilowatt of cooling, and putting that to the south. Well, that chiller to produce 100 kilowatt of cooling will actually have a compressor and a cooler that sends out 130 kilowatt of heating on the roof into the air. So instead of paying for 100 kilowatt of heating and 100 kilowatt of cooling, you could only pay the electricity for the cooling, which is a COP of 3, so it's only 1/3, and you get all the heating for free. So directly your energy bill goes down by 70%. But still, it will need 2 more copper pipes. Yes, of course, they cost money. How much is that? 1 month of energy use in your building? It's nothing. So there's a lot of things you can do today to reduce your energy cost in existing buildings dramatically without too big of an investment or without inventing the wheel one more time. Now, future, of course, matters. What is your carbon footprint we talk about? How much CO2 emissions do we have? And I think this is also an issue. Somebody said, we want to be more green all the time. I know companies like Gazprom that work with energy, like we are what we are, you say. Of course, energy is dirty. They want to have a green appearance, because if they want to produce energy and export outside the country to earn money, they cannot be a dirty company. They have to be a clean company. So it's about the image, it's about the effort. How clean can I be? How efficient can I be? That's really important. And of course, we talk about knowledge. Air Academy, you said there was more than 500 articles on the Air Academy homepage, where you find anything on how to save energy, how to use solar power, how to be more efficient, how to integrate certain technical aspects. It's all there at your fingertips for free. So you have to use that. I want to close off giving you some examples. It is a retail project, how to save money on that. We built over 100 little shops in making it as efficient as possible. This is standard retail. And we compare traditional constant air volume system with a demand-controlled system, where everything is demand-controlled. And as you see, the fan power per year will be 41 megawatt hours in a traditional system. And then the heating, 46 megawatt per year, and cooling about 10. Well, in the demand-controlled balanced system, you see the fan power goes down to basically to 10 megawatt per year. That's 4 times less. While the heating is about half, and cooling is roughly the same. So if you look at these comparisons, you see that the total cost goes from, and sorry, this is the problem with the presentation, it all messed up with the projector. It goes from 8,500 to 2,500. So it's a huge cost per year. They save about 6,000 euros per year. 6,035 per year. Well, on top of saving this annual money per year, now you wonder, okay, how much more will the investment be for such a plant? How much more expensive does every shop get? Now let's look at that. Here you have an investment for the district heating, and you need a water chiller. Over here, you have no district heating, and you need a reversible chiller and heat pump, which costs you roughly the same as a water chiller. So investment so far is the same. On top of that, you have 20% smaller ducts, 20% less air diffusers, and a 20% smaller air handling unit. Now, I wonder if you should have a solution that is DCV, demand controlled, or CAV, which costs you 6,000 euros more per year. I'll give you another example. If you go to an air handling unit and you integrate the different components inside an air handling unit, we're talking about the rotor only and about cool recovery. Now we compare an air handling unit with a standard rotor and without cool recovery. And you will see that here you will need, in Rome, Italy, a big unit, you need to install a cooling battery of 400 kilowatt. So you need a chiller that takes care of 400 kilowatt. And the running cost for a DCV or a VAV system per year is accordingly. Now, as soon as you have cool recovery, so you actually use that the indoor air is colder than the outdoor air, so you pre-cool the air with the extract air, this number goes down to about 300 kilowatt, so 1/4 down. And of course, the energy use per year goes down as well. Now you add the sorption rotor, and the sorption rotor costs you, I don't know, Sergei, a couple of rubles in comparison. It's nothing. The sorption rotor will recover the humidity. In places like Krasnodar, extremely interesting. We're talking about 30% saving. St. Petersburg, it's around 8% saving. But here in Rome, you're down to 199 kilowatt installed cooling power, which means half the size of the chiller. So this is a direct saving of 25,000 euros just on the chiller for a sorption rotor that costs you a couple of hundred or a couple of thousand rubles. It's quite interesting. And of course, the running cost, as you see here, it's up to 17,000 euros cheaper per year on top of that. So with the integrated design, you actually save energy per year, but you also save installation cost. It doesn't have to be more expensive from the beginning. Quite interesting. However, if you make a system more complex, if you look at a hotel, for instance, I think you will learn this afternoon something about what the Swigan calls WISE. It's a demand control system for heating, cooling, distribution in the room. You will see that you will invest more money on room level at least. So even there is a rule of thumb. If you talk about investing roughly 10% more on the whole system, you will save roughly 35% of energy per year. And that's, we have calculated it in many different projects, and it seems to be true quite often. There's an investment calculation for Victoria Tower, it's a big hotel, that they had the payback time for this DCV system within 2 years almost, 2.04 years. So that's quite nice. We've made one project in Glasgow in England, Erskine Bridge Hotel. 180 old rooms, actually it's 196, but I calculate 180 because it's easier. So it's an old hotel, it's overheating, it's old gas boilers that start to fail, and you have no cooling in the summer, so it's getting very hot in the rooms. And so they have high energy bill, they have problem with the technology, and the rooms are too hot. So what we did, we have an existing extract air system from the bathrooms, and we change it to a balanced situation, heating and cooling and ventilation on a balanced system. And here you see the numbers. Total heating need, 500 megawatt hours per year for the whole hotel, while today it's 116 megawatt hours per year. On the cooling side, we don't have the cooling there because it was not there from the beginning. The cooling is extra for free then. You have the transmission is the same because we didn't change the building. And then you see the tap water is the same. But here you see the total heating cost going from gas to electricity by the heat pump. The energy bill goes from 33,000 euros per year to 9,000 euros per year. So the energy bill is down to 1/3 as it was before. Now that's good, right? You're saving actually money there. But then on the tap water side also, from 160 kilowatt you go to 58. So you see here the comparison. But you also have no comfort cooling on this side, and here now all the rooms have comfort cooling. because they have a swimming pool, they have the showers, they have a lot of excess heat they can use to produce cooling. Now, the average room rate for this hotel was 50 euros per night. And I'll ask you, if you have no comfort cooling and now you go to a nicer room with better climate, how much can you raise the room price, do you think? Anybody? From 50 euros to, what do you say? 70 euros, I hear here? Okay. Now, I asked the owner, is it okay if I give you 55 euros per night? Only 5 euros extra. Yeah, that's very little. But okay, we keep it like this, okay? Now, the occupancy rate in the hotel is currently around 70%, which means 7 out of 10 rooms are rented, 3 rooms are empty. Can you increase your occupancy because customers come back because they're happy? Yes, you can. How much? Oh, he says 85%. No, it's too much. I give you 75%, 5% more, okay? Now, this is important, ladies and gentlemen, because when you talk about integrated design, you're so focused on cost all the time. You have to look on the profit side also. Now I show you what happens on the profit side. With this calculation, and you can do it by yourself if you don't believe me. The annual energy saving is 24,000 euros. That was nice, right? But the 5 euros extra per night and the 5% extra of average occupancy will end up with an extra 410,000 euros per year in profit. That's 410,000 extra in the pocket of the hotel owner he didn't have before. So it's fantastic that we saved 60% of energy, but that number is only 24,000. That's 20 times as much on the increased profit by increasing the indoor climate. Now, I was always told you cannot tell people the value of indoor climate. Yes, you can. That's interesting, right? That's a nice number, and that's an argument how to finance and how to build the right installations in your buildings, because the money is there. And we showed them that this means with a 20% of own money and 80% from the bank, they can spend 2 million euros for refurbishment to have a payback within the same fiscal year. So when the books are closing in the end of the year, they will still have a neutral result on including the whole ripping off the old stuff, putting in the new stuff. So of course they can afford to do that. That's quite interesting. And now we also will hear this afternoon, there's a tool called ESPO, and you will hear all the technical details about it. And I will not tell you about it, but it's a simple tool to quickly for you compare a CAV, constant air volume solution, with a demand controlled solution. It takes 5 minutes if you're good at it. If you're not, it takes 15 minutes, which is still reasonable. I've been teaching these courses for ESPO that take 4 hours, and you can work with this program freely. So today you will just get an introduction to that. But that's very, very simple. So simulation through the building process. And what you can do here, you can make power calculations, how much power you have to install in a room to calculate the size of your chillers, heat pumps, and so on. You can look at the energy consumption during the year. So you know month for month how much heating, how much cooling, lighting, and so on and so forth. You can make it for the room level or for the whole building. And you can also compare, for instance, a CAV, a DCV, and a VAV solution. All the energies, heating, cooling, ventilation, lights, it's all there. This takes you a couple of minutes. Making a decision what kind of system you should bring into that building that you're currently working with. If it's an office, a school, whatever, municipality building, it's very simple. And if you would work with PM vent equipment, you can even have direct links to all the products. But important to say is you can use any product from any manufacturer with this program. You don't have to work with Svegon products. It's just easier because they're already predefined. But you can put in there any chill beam, any heater, any cooler from any manufacturer in the world. And it will make the same calculation for you as you need it to go along in your project. And of course, you can design any kind of room you want. So that's the idea, that you can very quickly calculate the payback time for demand control systems. You can see what a higher comfort level is doing for you in terms of payback. You can optimize the size of heating, cooling, ventilation, ductwork to save money on that. And you can make comparisons within minutes. So you don't have to have either ICE or very complex data engineer 10 days. No. We're talking about very short time, and you can all do that. So that's nice. So integrated design. Basically, you have the motor, which is air production, heating, and cooling. You have the logistics. This is all the dampers and the silencers and the valves. You have the diffusion, which is grills, beams, comfort modules, and so on. And then all of that is connected by integrated controls to have the right, and then all of this is also connected by the right facilitators on the side, which is cables, ducts, and pipework, to bring the right amount of air, water, impulses, and so on to the right place in the building. So, what's the meaning of good indoor climate? Here you have your rental income, you have your cost, and you have your profit. Because in the end, somebody has to pay for it. It's your end user. It's the wallet, all right? So, if you increase your rental income, that's more profit. But of course, you can even save more. Because even if you look at this way, you have your investment, you have your maintenance, you have your energy cost, and you have your profit. And now you put a better installation, the installation that we're talking about, demand controlled, integrated. So you spend 10% more money up front in your investment. And you will save roughly 35% of energy on annual basis. So the LCC, the life cycle cost, will still be in your favor. And you save the polar bears on top of that. So that's good. So it's a higher profit from operations and a higher real estate value that you have. So to conclude, integrated design, as I see it, is the early integration of architecture and HVAC concepts is a necessity. Location, installation, definition of climate and space. Take care of that from the very beginning. Invite the architect or be invited by the architects to be there from the day one. And of course, the technical design that fits to the architecture and makes the perfect indoor climate becomes invisible. So if you all want to be invisible, then you made a perfect job. And you get paid a lot of money. So that's a contradiction in this, right? So basically, this is what I wanted to tell you about integrated design. And I thank you for your time.
Thank you, Markus, for a wonderful presentation. And let me apologize to you for Markus. We have integrated design, HVAC, and architecture, and we have data centers. Mm-hmm. How do you combine it? Maybe it's a question for both of you. Can those systems have a synergy or something?
Of course. I mean, if we talk about synergies between architecture, HVAC, and data centers, I think Morgan was in there already a little bit. Imagine you produce a lot of excess heating in your data center. Well, normally there will be some kind of office nearby that will need heating. So first of all, you could use part of the excess heating to heat the office.
Definitely.
For the other part, as you said, by integrating the air handling system in a different way, you can be much more efficient, not just by placing the diffusers, as you said, but also at how do you produce this energy, how do you produce the air, how do you reuse the energy.
And reusing the energy is one of the biggest problems when it comes to efficiency in the data center. If you have an office close by, that you can use the excessive heat to reuse that, that's when you get it more energy efficient. Mm-hmm. As it is now, most of the data centers are pumping the hot air out in the air. It's a very few initiatives I have seen around the globe where we are reusing the hot water.
Then there's one other option as well. If you're thinking about this, you will have a presentation on the gold unit later on. Normally you would use a gold unit to bring fresh air and recover the energy into a building. But what we've seen, that they actually have used the same units, but connecting the ducts in a different way. And by that you use the outdoor air over the rotor to cool the return air in the data center. So you don't actually have to bring fresh air to the data center that you might not want to do because of the control of humidity, amongst others. But you can actually use the outdoor air over the rotor to connecting the other side of the duct and cooling the outdoor air, cooling the extract air from the data center with the outdoor air without mixing the air volumes. With the rotor, extremely efficient. So yes, there's a lot of synergies that we could work with.
Definitely. And a closed air system is what we prefer in the data center. We don't want outdoor air coming in because it can contribute to pollutions. It can be smoke. It can be anything except from the damp or the humidity.
And also what we see in some countries now that actually data centers are selling their excess heat back into the district heating. That's also a part where you have integrated design.
Yeah, we have seen that on experimental occasions only so far. We were heating up a swimming pool or a swimming school, all that.
Right.
Thank you.
Thank you. More questions? Oh, yeah, I knew you would have a question. Are you going to ask
Okay. Thank you. Здравствуйте, спасибо, очень интересная тема. Я услышал, вы сказали, что желательно для экономии электроэнергии, ну и любой энергии, сбавлять давление в системах. В системах переменного расхода давление, как правило, выше, чем в системах постоянного расхода, для того, чтобы поддерживать баланс, когда один клапан закрыли, воздух пошел в другую сторону, чтобы воздух балансировался правильно. Но мы имеем более высокого, таким образом мы имеем магистральное давление выше. Отсюда вопрос, как вы ловите баланс, как вы делаете экономический расчет, делаете ли вы его, насколько, это не слишком ли сложная задача?
It could be complex, yes, if you let that to be done by different component providers or manufacturers. If you go to one manufacturer that delivers the whole system, you will also get the integrated controls, how to control these pressures. Now, this Air Academy feature is not about talking about a certain provider, but of course a provider is here by PM Vent, and PM Vent will tell you that they have a system called the WISE system, and what they do with that is that they have linked up all the dampers in the diffusers on the corridors, on the zone level, with the central brain, what they call the supervise. Okay? But it could be another brain, it could be another brand, then there's a different name, it doesn't matter, it's the same idea. So what you do is, if you imagine this room has to have enough capacity for all of you in here in the middle of summer. So this room needs a lot of air and a lot of cooling power. Well, now it's not in the middle of summer, but you're a lot of people in here, but you already now need less cooling power. So this room in 99% of the year will not operate on full power, okay? Which means normally that the dampers would be closing, the valves would be closing. And that is true for the different rooms in this building. Now what happens is central brain, in this case the supervise, will check all the positions of all the dampers. And it sees if the damper or the area that needs most energy, it's only 50% open. What it will do, it will open the damper 100%, low pressure, and it will send a new pressure point to the air handling unit. So the air handling unit will slow down, okay? So the difference is on pressure control system. This is a big, big difference. The air handling unit is not running on constant pressure. The air handling unit is pressure controlled. This could be 200 Pascal, 190, 180, 250, 160, depending what it needs right now. Because the dampers should be as open as possible, and the pressure impulse that goes to the air handling unit goes up and down. And by that, the air volume in the building goes up and down. But the dampers should always be as open as possible. So if this room is 50%, and that room is 20%, then this room should be 100%, and this room should be 40%. So yes, you still have some pressure over there, but much less than before. So you reduce the pressure as much as possible. And by that, the fan power goes down. SFP goes down. If you imagine you have a duct, and you need a certain amount of air going through the duct, and you reduce the air volume to 50%, the amount of energy is times 8 less. It's to the power of 3, because pressure goes down in square, and air volume goes down half. You understand that? So reducing air volume and pressure at the same time is not only half the energy bill, it's 1/8 of energy bill. It's only 15% left. So the money go down very, very quick. So that's why it's very important to work with a low pressure and variable air volume. Is that an answer to your question?
Как я понял, вы доверяете поиск этого баланса компьютеру вентиляционной системы. Баланса давлений, баланса расходов. Правильно я понял?
It's two parts. The whole building has to be in balance, of course. So supply and extract have to be in balance. But the extract in this room will follow the supply. It's a slave control. The damper knows how much air goes out. So if this is now 400 cubic meter going in, over there it's 400 cubic meter going out. Now this one goes up to 500. This one will go up to 500. This room will be in balance. And the rest of the house will be in balance. So you don't get overpressure, you don't get under pressure in here. But the amount of air that comes in here is based on the need. How many people are you in here? How much are you breathing? What is the air quality? What is the temperature? And of course I have to trust the controls, because we do that every day. I mean, if you drive your car, you trust the controls. If you have a washing machine at home, you trust the control to make your washing clean. Without controls, it's just a fan in a box. It's nothing. It's not even working.
Okay, thank you.
Okay.
I'm sorry. Я просто еще вот хочу добавить к тому, что сказал Маркус. Нужно понимать, что система WISE, она оптимизирует работу вентиляционной установки. И за счет того, что система GOAT, она позволяет очень плавно менять расход воздуха в зависимости от того, что требуется в помещениях. Сегодня вы услышите доклад на эту тему, и там будет более подробно рассказано. Но на самом деле командуют, если так можно выразиться, всем помещениям. То есть если у вас стоят там различные датчики, они могут быть датчики присутствия, температурные датчики, то, что вам нужно поддерживать. То ли это будет какая-то сан-норма, то ли это будет температура. И будет выдаваться запрос из помещения на открытие тех или иных заслонок. И система GOAT будет реагировать в итоге на вот эту команду и убавлять или прибавлять расход воздуха. Вот, поэтому вот эта система WISE, она отличается от того, что, возможно, вы имели в виду, тем, что она более гибко работает по запросу. Понимаете, да?
Вы привели пример Франции, если не ошибаюсь, где там растут всякие грибки там и все остальное. Такой вопрос, вот, как бы в гостиничных номерах применяется система с переменным расходом. То есть при отсутствии человека клапана закрываются. Вот. Что в этой ситуации? Как бы нужно оставлять какой-то минимальный расход на объем этого помещения, чтобы там не происходило такого затухания, там, цветения, либо какое-то проветривание организовывать, как это в Европе применяется. Потому что вот в России я знаю отели, где эта система установлена, но, к сожалению, она как бы реализована и не работает, наверное, так, как задумывали проектировщики. Вот, потому что клапана закрываются в полном объеме, и в помещении прекращается какая-либо циркуляция воздуха.
Right. Now, again, for the hotel rooms, the rule of thumb that you should remember, thank you, the rule of thumb for the hotel rooms that you should remember is when the room is occupied, it should be around 80 cubic meters per hour of air change. Right? That is about 22 liters per second. Okay? When the room is unoccupied, it should be around 40, about half. Okay? So that already saves a lot of energy. It should not be 0. It should be 40. And 40 means 40 out from the bathroom and 40 into the hotel room. And then it's always extract from the bathroom, always supply into the bedroom. And then it's transfer air between the bedroom and the bathroom. It's standard, okay? But it has to be always in balance, less or more. And it has to be, as you say correctly, it should be ventilated all day, all night. And always from the bathroom, but much less. So one saving when nobody's in the hotel room would be to bring down the air volume. The standard hotel system, however, will have 80 cubic meter per hour constant all the time. That is the standard all over the world nowadays. But today, the idea is to save energy by reducing to 40 cubic meters, so about half. On top of that, what you do is you save energy by changing the temperature to non-occupied temperature in the hotel room. So if it's a 5-star hotel, you would accept 24 degrees in summer. If it's a 4-star, you accept 25. And a 3-star, you accept 26 degrees inside when somebody's there. While when the room is empty, you can accept 2 degrees more. Only 2 degrees more, because when I come back to my room, it should go quite quick to cool down again. So I cannot come into a room with 35 degrees. I will go, oh, sorry, I don't pay for this. Okay, but it's 28, I go in there, the cooling goes on. After 10-15 minutes, the temperature will be fine. And it's the same for the cooling. On the winter time, a 5-star hotel will expect 21 degrees. A 3-star hotel, 19 to 20. Okay, but nobody's in the hotel room. You can drop to 17 or 18. You come into the room, you put on the light, you put on your TV, and you come in yourself, and within a couple of minutes, the room go up to 20, 21. But you cannot go lower than that because it will take too long time because everything gets cold. The wall go cold, everything, the tiles get cold. So you save money by reducing the amount of air and by not climatizing the air as much. And remember, the air you bring inside, if it's in St. Petersburg in the winter, -10. If you have to heat 80 cubic meters of air per hour to 22 degrees or 40, that's a lot of heating power that you save. So that's why it's interesting to reduce the amount of ventilation when the room is empty. But never to zero, you're correct, sir. Okay?
Вы назвали довольно точные цифры доли технических помещений в разных зданиях. Там, я услышал, гостиницы там 17%. Вы не могли бы пояснить, какого сорта помещений участвуют в расчете? Участвуют ли здесь какие-то горизонтальные коммуникации? Это касается только вентиляции или всех инженерных систем, включая пожаротушение?
I'm talking about floor space, rentable floor space. How much square meters of, if I have a building of 1,000 square meters, how much can I use to rent to you? And how much is lost by shafts, by technical rooms, by connections, by ducts, by sewage pipes, by electrical pipes, and so on. So it's the usual rentable floor space. I have to sacrifice about 17% in the hotel, about 11% in an office building. Including fire protection, water, sewage, electricity, heat, light, ventilation, whatever. Okay?
Спасибо.
Большое.
No more questions? Okay, so Markus and Morgan will be here during the coffee break, so you have the chance to talk to them. If you are feeling not very comfortable in English, we will ask our lady to stand by you and translate for you.